I just want to introduce myself. My name is Felix, Principal Engineer and an Apache Spark committer. Like I said, Apache Spark committer, I've been contributing to Spark and SparkR for 2 years. I organized a Seattle Spark meetup, which is a pretty decent-sized group of community there. And I was a teaching assistant of the massive online course back in 2015 summer to related to Spark. So yeah, I mentioned Spark a couple times, so this talk is going to be about Spark. But this talk, just want to do a quick disclaimer. This talk includes contribution from the community and a quick agenda. So we're going to start talking about Spark and R and the architecture for SparkR. We're going to touch on the feature for SparkR. And then we're going to dive into the main topic for this talk, SparkR for data science, how do you do machine learning, that sort of thing with SparkR itself. And then we're going to touch on the ecosystem and quickly talk about what else is coming in the next release. So can I ask for a quick show of hand how many of you actually been using Spark for the last months, year? Maybe half of you. How many of you actually know about SparkR, have been using SparkR? Maybe 1 or 2? Great, we should have a talk after. But yeah, Spark in 5 seconds. This diagram, this chart always show up. Spark itself is a general purpose cluster computing system. It supports several different types of vertical, including something new like structured streaming, a streaming application, Spark SQL, data frame, data set, data sources, machine learning, ML pipeline, and graph. So as you might already know, some of these have moved on to slightly different organization. This chart hasn't been updated. For example, structured streaming is actually running on top of streaming and structured data, like data frame, data set. So R is a programming language for statistical computing and graphics, so like visualization, that sort of stuff. Its predecessor is S, which was created in 1975. S4 is kind of the latest iteration of it, and R is essentially S4 plus lexical scoping. It's an interpreted language. And it's really good at matrix arithmetics. And it has a really huge repository called Crane that has 10,000 packages. So a lot of things you can imagine doing is available as a package you can download. So today we're going to talk about Spark and R together in a package called SparkR. So what it is essentially a R language binding for Spark and Spark SQL. It exposes Spark functionality in R-friendly data frame-like APIs. It has its own REPL, so you can run it as a shell and sort of interact with it. And it could also be loaded as a library. And all you need to do is initialize a session called SparkR.session. So in terms of architecture, SparkR essentially is 3 different pieces coming together. The first part is the native R classes, the methods you interact with when you're using the package itself, the class and methods you call into. There is also a RBackend, which actually is implemented in Scala. It runs in the JVM process itself. It communicates between the R classes and RBackend using a proprietary socket communication. It also comprises of a set of helper classes for things more complex, things like a machine learning pipeline, that sort of thing, or a set of helper classes that kind of makes it easier for encapsulating that interaction. So the key advantage of this kind of architecture is that, as you can see, most and almost everything heavy lifting is actually being done in the JVM itself. This is a relatively dated benchmark from 2015, but what you can see from here essentially is one thing, which is regardless of the language binding you use, you get the same benefit that you get from Spark itself. Whether it's the catalyst optimization for your transformation or your SQL getting optimized, or leveraging tungsten and predicate pushdown or code generation, all these innovation that happens, you get it automatically through SparkR. So in terms of feature, there are actually a number of things that are pretty new. If you can see the green, which is kind of a little subtle to see here, there are a lot of new things since the 2.0 release of Spark. So things like Spark session support, catalog API for managing internal, managed, or external tables, or processing Spark packages, handling Spark packages, or adding arbitrary external files into your Spark job using the Add Files API, or install Spark, which is a single entry point where you can have it automatically download the matching JVM Spark release and work with Spark like that in a very relatively painless kind of fashion, or machine learning pipeline, or native UDF support, which these two we're going to talk about in more details. Something that's substantially newer is structured streaming, just coming very soon in the 2.2 release that hopefully is going to come out in maybe in a week or so. And then cluster support. We support all three different cluster manager in SparkR as well. So, like I said, this is the main topic for the talk, SparkR for data science. There are essentially two ways to go about doing this. Some things you need to keep in mind of if you're looking at SparkR and you want to use sort of a machine learning model to build a Spark application, you can think about whether this is something that inherently supported by the Spark ML Pipeline API, or this is something that you have an existing package, R package that you want to use, and you want to leverage the existing kind of experience and knowledge or expertise you have with something that you already are familiar with and use that instead. So we're going to actually talk about both approaches and follow down two different paths. So we're going to go down the right-hand side for now. So SparkR ML Pipeline. So what is a Spark ML Pipeline? Essentially is a way you can define a sequence of transformation and modeling all put together that takes your input data and then in the end either get a model back or leverage a model to deliver some insight at the end. So here's an example of it where you take the input data frame, data set that you have, apply it to a sequence of transformation like tokenizing the text and then doing hashing on the text itself and then passing it through to logistic regression to get a model back at the end. So as I mentioned, preprocessing, feature extraction, model fitting is inherently part of the ML pipeline you can build right now with Spark. So with SparkR, one thing kind of innovative in a way that we were actually packaging up this ML pipeline that you can build and deliver a set of simple, easy-to-use API that may be very familiar to a lot of these existing ML packages you can get in R. So for instance, if you look at looking at doing a topic modeling on text that you have, right? So you may have a LDA method which takes the plain text, and then you want to actually build a model out of this. So the API you see on the left-hand side here is the SparkR API for LDA. So you see there's a text parameter, there's a K in terms of the number of topics you want to get, and the number of iteration, and so on and so forth. What it does under the cover is actually build this ML pipeline for you automatically. So what you see on the R side translates to what you see on the right-hand side, on the JVM side, where there's, in fact, a ML pipeline can actually get built automatically for you, which takes your text data, tokenize it automatically, applies stop word and remove them, and then vectorize the count and so on and so forth before passing it to LDA. Could you imagine you have to do it yourself? Then you have to build all these steps and then into a pipeline and then apply it to the data before you can build a kind of usable model out of this, right? So in R, SparkR takes care of all of this for you. And once you have a model, there's a number of operations you can perform on the model itself. You can take the model and then get a summary out of it. The summary will be useful for evaluating performance of your model itself. Or you could actually take the model in a lot of cases, in almost every case, there's some exceptions, where you can actually take the model and apply it onto the new data itself. Or you can actually go persist the model, and then retrieving the model in a separate job itself. So SparkML in SparkR 2.0. So in the 2.0 releases, we actually have 4 machine learning models that we support in SparkR. Whereas in 2.1, we have grown from 4 to 13. And in fact, that has continuing to be an area that we are making more progress on. In Spark 2.2, we have a couple more that we're adding to the mix. So it's becoming quite a collection. But before we dive into all these SparkR API and how to call into it, one thing I want to spend some time talking about is the R formula support in SparkR. So if you're familiar with using building machine learning model using R, you might already be familiar with the R formula concept. So the idea here is you can specify the model using the symbolic form you see here. For in this case, R respond is model on F0 and F1 using this notation. And in Spark, we support a subset of this, which is quite a bit also. And then this support for our formula actually is implemented, if you remember the ML pipeline diagram here, that actually becomes a transformer that sits in front of everything else. What that means is, in effect, you can go back to other languages that is supported by Spark, like Python and Scala and Java and so on, and then use the same R formula support to signify the feature you want to go into this machine learning model and so on. There's also a number of syntactic sugar that you get automatically for free by using this R formula symbolic form. For example, the label column is automatically indexed for you, similar to what you get in native R. The term column is also one-hot encoded if it's a string. And so here's an example of the R formula actually used in the API for GLM. So there are, in fact, 2 versions that is implemented in SparkR. The first one is the signature very similar to the native R signature. You can call GLM with the formula you specify, pass in a Spark data frame, and then specify the family. This syntax is exactly the same as what you get in R GLM. There's also an alternate form where, when we discuss in the community, there are options and parameters you can have in Spark that you don't get in native R. So we have the second form where you can actually pass in all these alternate parameters. So you can do Spark GLM with a slightly different ordering of parameter, but there's additional parameter you can call into as well. So here you can see we support Gaussian and we have binomial. We also have other family that we support as well. And then you have native base, right? So naive base API you can call into, or you can have K-means, or you can have AFT survival model, and isotonic regression, and then GMM, alternate least square. One of my favorite thing, multilayer Perceptron model. And you can see, you can actually specify the hidden layers and all these parameters in a very simple parameter that you see here. Multiclass logistic regression. Or another of my favorite, random forest. So with random forest, you can do regression and classification using very similar APIs. You can specify the feature using the R formula. Again, you can see here. Classification automatically label the predicted label back into string so that it's much easier to read. Another similar tree model you see here is gradient boosted tree. I just want to also give you a taste of what are the parameters here. So when you look at Spark random forest, you can have the previous example I have, which is specifying a few simple parameter. Or you can leverage all these different optional parameters you can specify with Spark, like things like feature subsetting strategy, checkpointing and things like that. You can specify using the same API, and they're all optional. So some of the challenges with SparkML and the SparkML API in SparkR is that there's always a limit of how many machine learning model that we have and support. And sometimes it's challenging to keep up with new models being added to Spark, but we're actually really close now. I think we are, except maybe one or two notable omission with some limitation in terms of what we can do in R, we have almost everything. Sometimes it's non-trivial to map the R API into a pipeline model, so we need to figure out how much of these are optional parameter you can specify, how much of these are something that needs to be required, something we're doing automatically for you, that sort of stuff. And the other thing to consider here is because the way we implement a single API for these modeling cases, sometimes you do want to have the flexibility of the ability to specify your own ML pipeline. So this is something that we have a JIRA checking, and I'm really encouraging you to hopefully work with the community to see whether we can figure out how to support flexible ML pipeline going forward. Debugging is generally somewhat challenging when you're dealing with a cluster especially. So we also implement a bunch of error handling in SparkR to improve that. Hopefully, going forward, we'll do better as well. So if you remember the previous diagram, there are two different paths to go. So the other path you can go is if you have an existing package you're really familiar with, that you know what it does, and you trust it is going to do the right thing for you. One thing you can do is you can actually call into it using a native UDF. So UDF is basically the ability to specify the custom transformation you want to plug into these data frame execution using your, for example, in R, the language that you favorite, and implement your custom code that way. And there are actually two ways you can do this. You can apply the UDF by partition or by group. Essentially, how it works is like this. So if you're familiar with the concept of partition in Spark, the idea is your data comes in, it gets automatically divided into small pieces called partition. And for each of these partition, it gets serialized and converted into a native R data.frame, sent to the R process, and then into your UDF that is implemented in R. And you can do whatever you want in this UDF. And then at the end, you're expected to return a data.frame back, and the process can continue. And as you can see, that means your UDF is actually executing in parallel across how many partitions you have on your data set. And we'll get back to how that will be useful and that sort of thing in a bit. But when you have the UDF and you want to apply it across partition like this, the way to do this is called this method called dapply. The dapply method is very similar to the RApply family, where it takes the data set that you have, and then you can specify the function inline using sort of this anomalous function that you can define in here, where you can expect to get X, which is a native data.frame. You can interact with it using all these operations that you're familiar with. For example, getting a particular column like MPG, multiply guided, add two columns together, or add new columns, and then returning back that data frame. What we expect to get from you is that data frame, but also a schema that you need to define to make sure we understand what's being returned. But there is a variation here where you can also call dapplyCollect, which at the end of it will give you back a native data frame. In that case, we don't actually need a schema. We're just going to hand you off whatever is being returned by your native UDF. So let's look at a deeper, kind of longer example of this. So let's just say you have some training data, you want to call dapplyCollect. You have this UDF you want to specify inline here. And then what you do is you call random forest. So random forest is a popular random forest package in R. And you call it using this namespace notation. And all these parameters, very similar to what we've seen already with the SparkR version of this, where you specify the formula here and some parameter in terms of the number of trees, that sort of thing. And then after you train that model, you apply it onto a separate data set called T. We'll get back to that in a bit. And then we get a set of prediction, and with the prediction, we turn back this prediction we get from the UDF, and then we continue on. One thing to notice here is the UDF, where we talk about T is actually a local data set that get something called closure capture. So we automatically detect the fact that you're referencing T. That gets serialized automatically for you, distributed across all these parallel processing. That happens when we look at that diagram. So this is sort of a syntax sugar for you to automatically does these things. So you don't have to worry about how to distribute all these things. So there's also a second option, which is you can apply UDF by group. So what you can say here is you can call gapply on the data set. You can say which is the grouping columns or columns you want. So in this case, I want to look at all the cars and then group by the number of cylinders it has. And then you can have a UDF that you specify in here, also inline, but takes one additional parameter, which is the grouping key. And then you can interact with it and return that data set. Same thing here. You also have an option of calling dapplyCollect, which does very similar things, except that you don't have to specify a schema. Some of the things you want to be careful about is when you return data set from the UDF, you need to make sure you understand how the data types maps from R to Spark or to Scala, I guess. So this is kind of a partial table of it. A lot of it is basically pretty straightforward, I guess will be as you would expect. For example, numeric maps to double. So some of the challenges of UDF. We don't have, as of now, support for nested structure as columns. And then when you look at particularly applying a UDF by group, what if your group turns out to have most of the data in it? You could run into a problem where you have data skew, where everything is piled into the same partition, and then overwhelming the native R process. You also have the potential for the flip side of the problem, which is you might end up having some group that doesn't have enough data or enough variation of data to process or build a model out of it. So something to be aware of. The other thing to be aware of is we're talking about cross-language, cross-process processing. So there are some fixed overhead in terms of serialization, deserialization, and data transfer, especially when you have these closure capture and you have this big native data set that you might need in your UDF. That might be too automatic or too transparent to you. You might need to be aware of kind of how to handle those cases. There's also the concern around package management. So if you're calling a native R package, you do need to make sure that it's actually available for your UDF to call into on all the worker nodes when your job is run. Spark doesn't quite handle that for you, but there are some tricks to do it. For example, like what I have, if you either load the package or install the package inside your UDF before you go, and then you reference it using the namespace notation instead of going assuming it's actually there. So that's probably the way that I would suggest to go. There's one last option we want to talk about here is that with UDF, there's also a third way to do this that's really similar to the R native L apply. So this is very good for something that is things like embarrassingly parallel type of task where you have these things that you want to just execute it across this big Hadoop cluster that you have all at the same time. So the idea here is you take a list of vector in R, and for each of these elements, we're actually going to execute in parallel, pass it to your UDF, and we expect to get something out of UDF that we're going to return back to you. So this is a slightly more elaborate example. So the idea here is this. So if I want to try this SVM model with different cost value, so what I can do is do it in this first line here, generate a sequence of value to try, pass it onto this function I defined here using Spark.ml apply. What it would do is pass each of these individual values to this UDF. And all of these will execute in parallel across the big cluster you have. At the end of it, you get this list of summaries you can evaluate in terms of the performance of the model and in terms of what cost value give you the best result out of this. So let me do a quick walkthrough here. And this is a demo that is also available. So this is going to be a quick demo. So I have this SparkR package running here. And I'm going to make it smaller. So you can also see the Spark configuration using the SparkR.conf API. You can actually get some help as well. So this is the built-in help that we build with example code and result. You can actually take a look at what is available, how to use SparkR. The other thing you can do is you can load existing data using read.df. You can print out a schema. You can take a look at the data using head. You can do join or combine the two data frames together. Or you can build like a temporary view where you can run SQL queries on this. So this is a SQL query where we're doing a somewhat decent one where we're grouping by values, where we're computing an average of essentially flights data. With that, you can also build a histogram. And then you can actually plot that as well using something like ggplot. So you see, everything is kind of integrated together where you can actually plot this as you go and visualize the data you see you're interacting with. You can filter data, or you can use something like MuckRitter where you can do piping between operations. So you can have basically combine filter and count all together in a single line. Or you do things like group by and aggregate across different dimensions you're looking at. Other things you can do is you can build additional feature. In this case, you can create new columns using these criteria. And then you can take the data set and then split it into different training set and cross-validation set. And we were looking at random forest before. Now we're going to run the UDF using the code we were looking at before. Right? Calling into the random forest API. And it's going to do that, and then you get the result back, and you can take a look at the prediction for these different carrier. All right, that's it. So that was a really quick introduction or demo. All of that is available for access later. It will be in my slide. The very last thing I want to talk about is we talk about SparkR as a package, can be loaded in IDE, in RStudio, and so on and so forth. One thing the community has been working really hard on is the ability to actually do this one-line installation for Spark. So the way this works is you could install the SparkR package, and then you call this API, which automatically download the official release of Spark, and automatically caching it and then manage it for you. That is in fact available since Spark 2.0. With that kind of support of packages, what we can do is support additional packages that depends on the SparkR package. For example, the SparkR X package is available out there that depends on the SparkR package itself. And to support this kind of activity in the community, we also have special APIs where enable you to call into the Spark JVM backend. So a few things about the ecosystem. There's other packages like SparkR. Our server has a RX Spark support. Apache System ML has a R-like API. And there's also a new package called R for ML, which brings together SystemML and SparkR together and figuring out what is the best tool for different type of things in terms of data processing or machine learning, that sort of thing. And so to recap, SparkR 2.0, 2.1, 2.11 release, we have Spark Session, ML support, GLM, UDF support, number of partition APIs call, several other things. But what is coming in Spark 2.2 is also very exciting. So we have several new machine learning APIs or model we support, including Bisecting K-means, linear SVM, GLM also have support for Tweedie, and FP growth and decision tree are added in the new release. Several other things we have, and like I said, also we have structured streaming support here, and a very essential API like checkpointing for data frame or catalog API for looking at your tables, databases, or just to refresh your table when your data is updated. It's kind of essential. So I want to leave you off with this one example I have with structured streaming. This is slightly off topic from what we have, but there's a reason why I mentioned this too. So if you're using MacReader and you're using this pipe notation, what you can do is you actually can build up a stream from Kafka using the SQL expression that we are already looking at, in the demo or before, and group by this column. And what I have here is a single line implementation of streaming word count. And I have another talk that talks about how you can do structured streaming and machine learning and UDF together, which leverages this part of this talk and the structured streaming talk. And so look forward to that. And thank you. This is the end of my talk, and I will take some questions if you have any. Thanks.
So my question is, well, I have two questions.
Yeah.
First is, if I have a R package that's all written and I want to take advantage of SparkR.
Mm-hmm.
It's on. Oh, there you go.
There you go, much better, much better.
So it's unless it's like a random forest, easily parallelizable,
Right.
is my only option rewrite the whole algorithm in Scala or something, or is there some way to port it?
Right. Well, it depends on, so the way I think about this is it depends on your need, right? If your data set is naturally applicable to, different subset of data, you can use something like Spark to basically orchestrate the parallel processing of it using different, aggregate, different level of aggregation, right? Like maybe aggregate a different level or using different dimensions that you use to give you different data set that you can parallelly execute it, using the example I have here calling the UDF with different grouping or different partitioning strategy, that sort of thing. If you actually need to have the full set of data, then the challenge you have here is your package might not even work, in a single machine, right? Like you may have maybe very granular data that has like hourly data or minute by minute of data that's kind of too many rows to fit to for R to process. For these kind of things, you generally need something that like a machine learning algorithm that actually inherently is parallelizable, so that it could work with Spark in a fashion where it could look at a smaller subset at a time and then kind of put things back together in that kind of distributed kind of manner. So so it depends. So.
Okay. So that sort of leads to the second question.
Right.
Let's say I can parallelize it to different clusters.
Yeah.
So each one may be done, using some memory and speed, which is fine. But if at the point is a single R session, I have to eventually get it and combine them somehow.
Right.
Now, is that limited by the memory in my laptop?
Actually, no. So the good thing about what we discussed today is that using the mechanism we described today, your processing actually, let's just say you have native code and you have native packages, and you are able to figure out what is the right way of splitting up your data in a way that would fit in memory or things that would make sense. And then you have it parallelly processed using the UDF this way. What you get back at the end is all these pieces combined into a Spark data frame. So in other words, you're not actually, unless you're doing a collect at the end to bring it all to your driver, to your laptop, you are not actually restricted by how much you can process by a single node. So after doing this UDF and the processing in parallel and so on and so forth, what you get back in this Spark data frame, you can further process it either right into permanent storage, so you can inspect it, or you can divide it into partition, or inspect it in like maybe sorting it and look at the performance and things like that, using all the data frame operation you have access to in a way that is not limited by traditionally you would have to put everything and load it in memory into your local R session on your laptop to see it, right? In this case, you don't. Does that kind of make sense?
Yeah, I guess.
Right.
And so I promised two, but let me add one more.
Okay, yeah, go ahead.
So this is related to data pre-processing. All right. So we have, you showed us some nice machine learning algorithms.
Right.
Now, instead of let's say regression itself, before that, I want to do some pre-processing. Right? Replace all missing values by the average.
Right.
Now, if I have a huge data set which is divided into clusters, right, I need some way, again, to get some information from each cluster back to them. Do I have to get it back to my laptop again, or can it be done directly?
So the good thing about Spark is that, in terms of doing machine learning with Spark, one thing I really like about it is you can basically have one application that does all these things. You could, ingest it using Kafka or any sort of streaming means or loading from this. For example, what I have is pre-process it and then split it into like generating new columns, and then split it into different set of data, like training set and cross validation, that sort of thing, and then run a machine learning model of it. So to answer your question, this is something that inherently supported by Spark and also by SparkR, is that you can do your data cleaning or even ingest the data from the source directly and do your data cleaning, manipulation, feature generation, all sort of thing in one flow. So you can have it in one application, using SparkR, and then feed it into your model, and then look at the model, what you're getting back, and evaluate which is kind of the best performance you get out of it, in one go. So this is actually something that's supported by Spark. So what I have here, right, just maybe in 10 seconds or so, we'll be loading the data, we're doing manipulation on the data frame itself, that sort of thing. Does that kind of make sense?
Sure, okay, thank you.
Yeah, you're welcome. Any other question? Yes.
What's the, for the data scientists, I think is another popular language is the Python.
Right.
So I don't know what's their position to compare, those two.
Well, so they're two really different things. I guess, all these popularity pool has indicated, I think maybe half of data scientists would prefer Python. The other half would be R. It's always a neck-to-neck kind of thing. There's no really clear winner between the two. My take of that is, I've been doing this with R for like 2 years. My take of this is, you want to stay where you are, what you're familiar with. So if you started in R, you're familiar with all these packages you have access to, you want to be able to stay in an environment where you can actually leverage all those things, the knowledge and expertise and familiarity, things that are already available, all those things in the same. That's why we have SparkR to enable you, like specifically with this talk, talking about how you interact with native packages in this way, in an efficient kind of manner. With Python, you can do similar things. You can do UDF, but UDF is actually on a per row basis. This is actually one of the biggest trade-off between the two. One thing that's kind of unique in the SparkR implementation is when you do UDF, it's not UDF per row, it's UDF per partition. So it's kind of more efficient that way. With Python, you can pass individual row into native Python packages like scikit-learn, that sort of thing as well. So there are kind of different and similar approach for similar things like this. In Python, you have the Spark.ml Pipeline APIs you can call into. You can actually build pipeline, very much similar to scikit-learn. In fact, the Spark.ml Pipeline API is based off of the scikit-learn pipeline implementation. So it's really similar in terms of syntax. And so you can do that in Python as well. So it's kind of, there isn't really a clear, winner between the two. I mean, the thing about the platform, what we have with Spark is that we will enable both. We'll let you have what you need to make it work. So.
Okay, thank you, Al.
Thank you, and I'll be around for further questions. So thank you very much.
We have to get ready for the next session. Thank you, gentlemen and ladies.